Okay, hi everybody. So far we've talked about rotation around a fixed axis, right? So in the previous example, we talked about a pulley that was fixed with a clamp, and the pulley was just rotating about that axis. But what about something which is both translating, it's moving in some direction, and it's rotating? So that's what this section is all about. So let's use as our first example a yo-yo, and we're just improving our modeling of the world. Now we can take into account both linear motion and rotational motion. So if you have a yo-yo, a string wrapped around this piece of plastic, and you drop it, does the yo-yo fall and accelerate at 9.81 meters per second squared? And the answer is no, right? There are now two forces acting on this falling object. There's a tension force and a weight, right? So from the force and torque perspective, we can talk about this yo-yo in that way. We can also talk about this yo-yo in terms of energy. And now we have both translational kinetic energy, meaning the yo-yo is moving some number of meters every second, but also it has a rotational kinetic energy, and we have to take that into account now too. So if we want to talk about this using force and torque, right, we can model the yo-yo just as a disc with a string attached to it. And to understand its motion, I could use both F equals ma and our rotational Newton's second law, torque is equal to moment of inertia times angular acceleration. So to do this, I'd have to draw my kind of modified free body diagram where I draw a dot to represent the center of mass of the yo-yo. Weight is acting on the center of mass, so that's not causing any torque. But then this tension force is applied at some distance away from the axis of rotation. So I'd have to show that this force is applied at some distance, and therefore it's going to cause a torque. And I'd have to take that into account using torque equals I alpha, and I could use these equations to solve and predict the behavior of this yo-yo and find its acceleration and things like that. But I could also model the system and talk about it using conservation of energy, right? Total energy is constant. Imagine there's almost no friction here, so the total energy of this yo-yo as it falls has to be constant, right? The total energy of the yo-yo now has a few additional components, though. Has both kind of a translational kinetic energy, just given by the fact that this yo-yo is moving, right? It has velocity, it's moving some number of meters per second, so that's my 1/2 mv squared kinetic energy, but it's also rotating, so I have to take that into account. That's part of the total energy now, so I have to add that term, 1/2 I omega squared. And it has a varying gravitational potential energy. As its height changes, its mgy is changing. So as this yo-yo is falling, its gravitational potential energy, mgy, will be decreasing, its translational kinetic energy will be increasing because it's speeding up, and its rotational kinetic energy will be increasing because the rate at which it's spinning is going to be increasing. Right? So as long as I take this into account, I can now use conservation of energy. If E total is constant, this quantity as a whole cannot change. It has to be equal to some constant. So therefore I can solve for an unknown. So these are going to be the two main methods we solve problems in this chapter. Force and torque together, or using conservation of energy, taking rotational kinetic energy into account. So a little bit more info on this. Again, if we're both translating and rotating. Translating, again, we're moving some amount of distance. We have displacement in some period of time and rotation. We're going to use F equals ma, but this is a net external force. We have to take into account all the forces acting on the object, both the forces acting on the axis of rotation and the forces acting at some distance from the axis of rotation. We have to take into account the total mass of the body, and all of these forces is going to result in acceleration of the center of mass of that object. We also have to take into account all the torques. All the forces acting on some distance, we have to add up all those torques, and that's going to result in angular acceleration about the center of mass. And then we need to calculate the moment of inertia of that object about its center of mass. Okay, and so this is how we're going to handle some problems. We can also solve problems using energy. So if I throw this baton into the air, the center of the mass of the baton is going to follow a parabolic path. The center of mass we could have predicted in chapter 3. Right? This is parabolic motion. This is just throwing a ball into the air. Right? It's exactly the same path. It doesn't matter that it's rotating here. Okay, but then this baton is rotating about its center of mass too as it moves through the air. So if I'm going to handle this, I need to take this into account. I need to do 1/2 mv squared, which is just the velocity of the center of mass, and this is the mass of the object as a whole. That takes into account the translation of the baton, also have to take into account the rotation about the center of mass. This is the moment inertia of the baton about its center of mass. This is the angular velocity of the baton. Okay, so really what we're doing here, since these are two scalar things, is just we're adding together two separate motions. We're adding together the translation, the fact that the center of mass is just moving, and we're ignoring any rotation. And so we can calculate the kinetic energy from that, and add to that the kinetic energy of just the purely rotational part of the baton, ignoring all the translation. Okay, and we're free to do that. So this is just an extra term we're going to have to take into account in this chapter. We also have to consider the rotational kinetic energy. Okay. Additionally, we can talk about rolling. If a wheel is rolling, it is both translating and rotating. So we can have both of these types of kinetic energy. So if I look at a wheel, I can again break up its motion into these two terms. Right? So at any given moment, if a wheel is moving in this direction, every part of the wheel is moving at that moment, has some velocity component in that direction in terms of translation. Okay, but it also is rotating, right? So the rotational part of this is the center of mass is not rotating. This part of the wheel is moving down. This part of the wheel is moving in this direction. This part of the wheel is moving up, and this part of the wheel is moving in this direction. So if I add together these two concepts, I get the kind of combined motion of the wheel, which the top of the wheel is moving really fast because the center of the mass of the wheel is moving in this direction, and the wheel is rotating about that center of mass. So the top of the wheel is moving faster than the center of mass. The bottom of the wheel is not moving. It's not slipping. Right? The bottom of the wheel is momentarily at rest because the center of the mass is moving in this direction, but the wheel is moving in that direction, and those two effects are canceling. So in that moment, the bottom of the wheel is not really moving, and the front of the wheel is moving, kind of has some velocity in this direction, right? Because the wheel is moving down, but the wheel as a whole is also moving in this direction. So if I add together those two velocity vectors, in that moment, the wheel has some velocity in that direction, right? So in general, we don't have to deal with that too much. We can talk about the kinetic energy of the translation, the kinetic energy of rotation separately, and we also have to add one special case here, which is the not slipping condition. If this wheel was just slipping, if this was ice, it wouldn't be rotating at all. We would just have this wheel just slipping in this direction. We'd only have to handle this part. But the fact that it's not slipping means we're also going to have the rotation. And something special happens in that case. If this wheel is not slipping, then the velocity of the center of the mass of the wheel is related to the angular speed of the wheel. Right? We know that the radius of the wheel times the angular speed of the wheel is equal to the tangential velocity of the edge of the wheel. Right? And if this is not slipping, the center of mass of the wheel is also going to be equal to the center of mass velocity of the wheel is also going to be equal to that quantity. So this non-slipping condition is going to allow us to relate angular speed to linear speed of a wheel. Okay, and we'll use that in some problems coming up. So let's do a couple quick clicker questions. These are fun, and I'll post some more videos on this later. But I have these two objects here, a solid cylinder and a hoop. The solid cylinder has a moment inertia 1/2 mr squared. If you look it up in a table, the hoop has a moment inertia of mr squared. It has a larger moment inertia. All for the same mass, all of that mass is distributed differently. More of the mass is far away from the axis of rotation. And the red line here is the axis of rotation. So if I put each of these at the top of a ramp and they roll down that ramp without slipping, which object will reach the bottom of the ramp first? So take a moment and think about that. Okay, so I'll move on to the next slide here. The answer here is A. So it turns out the solid cylinder is going to reach the bottom of the ramp first. Okay, we can understand that from an energy perspective. Both of these objects start with the same initial kinetic energy of 0. They're not moving or rotating. They both start with the same gravitational potential energy. They're both at the top of the ramp at the same height. They have the same gravitational potential energy. But as they roll down the ramp, they're going to be gaining both kinetic energy, translational kinetic energy, and rotational kinetic energy. Right? The hoop has a larger moment inertia, which means more energy is going to have to go into making that thing rotate, and less energy can go into translating it and moving it down the ramp. So this one ends up losing the race, this one ends up winning the race. It's easier to make this thing spin, it has a smaller moment of inertia, it's going to get down the ramp faster. Okay. To expand upon this, let's do the same thing now. Add to the race a solid sphere and a shell, right? So this is a solid sphere, this is a soccer ball or something, right? A thin shell of a ball. So which of these is going to get to the bottom of the ramp first? Is it, again, the solid cylinder, or will the solid sphere or the shell sphere get to the bottom first? So you can look at the different moments of inertia here. The solid sphere has a moment of inertia of 2/5 mr squared. The thin shell has a moment of inertia of 2/3 mr squared. So take a moment, think about this. On the next slide, we'll actually do a simulation experiment to check this. Right, so let's actually put all these objects on the top of the ramp. So I have I believe the red ball is my hollow sphere, the orange ball is my solid sphere, the green is my ring, my hoop, and the solid blue here is my solid cylinder. So when I get these going, let's see what happens. Okay, there they go, and looks like the orange ball wins, then blue, then red, then green. Okay, so orange won the race. The solid sphere got to the bottom first, then the solid cylinder, then the hollow ball, then the hollow cylinder. Okay, so the solid ball won the race. All right, so that was option C here. So why is that? We can see, looking at the moments of inertia, that 2/5 is smaller than 1/2, right? So this has the smallest moment of inertia. This won the race. Second place was the solid cylinder, which has the second smallest moment of inertia, 1/2. The shell has a moment of inertia of 2/3. That's bigger than 1/2, so that came in third. And the hoop came in last. It has the biggest moment of inertia. That's I equals mr squared, that lost. So the solid sphere is the easiest to get spinning. It has the smallest moment of inertia, so therefore less energy went into making it rotate, and more energy could go into making it just move down the ramp. So that won the race. Okay, so that's kind of fun. And you can see all these objects could have the same mass. The solid sphere would still win the race because the mass is distributed differently, right? Less of the mass is far away from the axis of rotation. With the solid sphere, a lot of the mass is along the axis of rotation, and therefore it's really easy to make that spin. With a hoop, all the mass is really far away from the axis of rotation. It's harder to make that spin. Okay. We can also talk about an object sliding down a ramp with no friction, like a hockey puck, or an object rolling down a ramp. Right? So the fact that it's rolling means there must be some friction, but the friction is almost zero with something that's rolling. That's why we use wheels in the first place. Right? So let's just say there's enough friction to make this thing roll without slipping, but there's not really much energy being lost. There's not much energy being lost due to friction here. So which of these is going to win the race? The hockey puck, which is just sliding down the ramp, part A, with no friction, or B, the hockey puck, which is rolling down the ramp. Which one is going to win the race? So take a moment and think about that, and the answer here is A. Right, so the hockey puck, which is just sliding with no friction, is going to win the race. All of the gravitational potential energy stored in this hockey puck is going to go into linear kinetic energy, and it's going to get to the bottom really fast. Right? With this hockey puck here, which has to roll down the ramp, some of its energy is going to go into making it rotate, and some of its energy is going to go into making it kind of move and translate down the ramp. And so since less energy is going to the translational kinetic energy, it gets to the bottom of the ramp last. Right, so in solving these type of problems, we're generally going to use conservation of energy. All of these objects have the same initial gravitational potential energy. We know the initial energy of the system. It's mgh for each of these. Right? At the bottom, they have zero gravitational potential energy. It's all kinetic. We have to take both the translational kinetic energy and the rotational kinetic energy into account to, again, determine which wheel is going to get to the bottom first and which wheel is going to have the biggest velocity at the bottom. Okay, so thank you.